Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Deanna Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I really love being a scientist. I love getting to work on really cool things and trying to understand what the universe is made of. And I love chatting to everybody about all of the cool things I get to work on. So for anyone who doesn't yet know Cup of Cosmology, the idea here is that this is an interactive show. The idea here is that you people can ask me anything you want about cosmology, about science, about space, about academia, about myself, literally everything. You can ask me anything you want, and I will do my best to try to answer all your questions. I see we have a lot of the regulars already coming in the room. We have Ben, Mita, Scott, Paul, Lethargo. I'm not sure if I've seen you before. Welcome if you're a first-time viewer. And David Howden. Great to see everybody. Welcome back to all the regulars. Welcome to any first-time viewers. It is great to have you here, whether it's your first time coming or whether you've been following for 8.5 years. You are welcome here on Cup of Cosmology as long as you have questions. And even if you don't have questions, you are welcome to come and listen to everybody else's questions and answers and me rambling about all the cool things that I find really interesting, which is a lot of things, actually. Whew, yeah, gonna be a hyper stream today, as opposed to my other streams that are chill and casual. If you haven't done so yet, please do like this video, leave a comment, subscribe to the channel, press all of the buttons on YouTube or Twitch, whichever platform you're watching on, make stuff happen. It really does boost engagement, and I really do appreciate all of you who leave me comments and who send me messages. It really does mean a lot to me that you still engage after so many years, or even first-time viewers engaging. It just means a lot that you will take your time to just take a bit of time to just like send a message, press buttons. Yes, you caught part of a stream once, but first full stream. Well, welcome to the first full stream. If you have any questions, do put them in the chat. The idea here is that you can all ask me whatever you want, and I will try to answer as always. I see some people in the chat here saying happy hump day. We are halfway through the year. That is indeed true. We are, according to the calendar, halfway through the year. Now, is it actually technically half? If we count, this was a leap year, so we have 366 days in this year. So if we want to get through half of that, we need to be 183 days into the year. Are we 183 days into the year? Or would that be tomorrow? Because there is a thing that there are more months with 31 days in the second half of the year. So while today is based on how we use the calendar, it's like the end of the 6th month, is it actually the exact half of the year? I don't think so. I think that's tomorrow. But in any case, we're almost halfway through the year. Tomorrow is July. Tomorrow is a good month because it starts on a Monday, and I just think it is very satisfying when months start on a Monday. There is no reason for it. I just think it's very satisfying. Your cat just ran over to listen. That is very sweet, John. I'm glad your cat comes to listen as well. That is really nice. I love cats. I love animals, so I'm glad to have cats in the audience as well. Whew. So, okay, there is no topic planned today. The idea here is that you can ask me anything, and based on your questions, we decide which direction this stream goes into. So you really have control over the stream and the direction and what we do with it and where we go and what we talk about. I have some vague ideas, some prompts that I leave for myself just in case you don't have questions. But this really is an interactive stream. You can ask, and I will try to answer questions. My brain might seem a bit tired and a bit out of it today, and that is because I have been on holiday for the last week and a few days. So I have not done any science in the last 10 days, and it has been glorious. Not the not doing science part, but the not working part has been really good for me. And tomorrow I go back to work, and I'm looking forward to going back to work, but it has been a much needed break. Also means I've not touched any science, so if there's been anything in the science news the last few days, I have not seen it. Question from Paul here. Do undergrads ever have the chance to get involved in work you do? I love that question. That is a very, very cool question. And the answer is yes. So there is generally sorry, I just got spooked because things have moved around in my apartment over the last couple of days, and something out of the corner of my eye looks different to what it normally does, but that's fine. That's okay. It's allowed to be there. It's a plant. Okay, so I think some people seem to think that you only become a scientist when, I don't know, you're doing your PhD or after your PhD. That is nonsense. You become a scientist the moment you start studying science. That is it. If you're applying the scientific method, if you're applying critical thinking to solve a problem, you're a scientist. Congratulations. You don't need an official title. You don't need a degree to be a scientist. So undergrads at university studying science, physics are a valuable part of the university system. Personally, I think teaching is one of the most rewarding parts of the job, and I love chatting to undergrads. Now, can undergrads get involved in the work? Yes. There are different ways this can happen. One of the easiest, or one of the clearest ones, is when bachelor students are wrapping, so undergrad students are wrapping up, they have to do a bachelor thesis. This is standard in pretty much most universities in Europe. I'm not sure about in the US. I think there's something similar. It's a research project you do to finish up your undergrad years. And yeah, if the plant has not directly moved by itself, but it's one that opens and closes a bit, so it does have some movement. But yes, it is on the shelf where it belongs. So when undergrads are getting ready to graduate, they do a bachelor's thesis. Now, the bachelor's thesis varies from university to university. The one that I did in Barcelona University was a 1-year project. Here in Helsinki, they're 3-month projects. So, of course, you get vastly different expectations on what the students should do in that time period. But it is often considered the first time students get exposed, or undergrads get exposed to the real, not real, to a research environment. Now, depending on the group, this will work in different ways. What we do in our group, hey Nina, great to see you. Welcome, great to have you here as always. So what we try to do in our university, and especially in our group, is when we have bachelor students, they are part of the group. They are welcome at all our coffee breaks. They are welcome at all our seminars. They are welcome to chat to everybody in the group. And during the bachelor thesis, usually what happens is the student carries out a 3 to 6 month project on a specific topic. Often to choose this topic, we have some defaults that we'll propose. The students are welcome to propose their own topics as well. And sometimes it's things like if I have something I want to look into that will take me a couple of weeks, but I don't have time to do it and it's not urgent, that is the type of project that is perfect for our bachelor students. And I've often found that we learn a lot from the bachelor students. It's like they acquire the knowledge and then share it with us. So the bachelor thesis is the first time for a lot of students where they can really get involved in our work. I currently am supervising one bachelor student. I have supervised 3 or 4 other bachelor students in the past. The projects have been very, very varied. There are some that have been more hands-on coding based. There are some that have been more of a literature review. There's someone who was more on the software side and helped us develop an interface for one of our codes that plays about that you can play with the code on a web page. So I've worked with a lot of different projects with bachelor students. And I think if done properly, it's a good environment for everyone because we get someone to help us work. They get some hands-on research experience as part of the curriculum they need to do this. And it's really the place where you can ideally give the students a good experience and show them the joys of doing research. There are other ways where undergrads can get involved with us. For an example, in our university, we have summer internships where every summer each professor will take on 1 or 2 students, and this is students from both bachelor and master's level. So the master's is what you do between the bachelor's and being a doctoral student or a doctoral candidate if you carry on in the academic path. I know in the US, for an example, the word undergrad often includes master students. Some places don't include master students in the term undergrad. So when I'm thinking about undergrads, I'm thinking about bachelor students who don't yet have their first university degree. But yes, we have these summer internship programs where the student spends 3 months, 2 to 3 months working with us. In my group, at least, we do pay them for this. This is not standard, but I'm very glad that we do because personally, I don't agree with unpaid internships. You know, you do it for exposure, you do it for experience. Exposure doesn't pay your bills. But that's a whole other rant. So we have these summer internships for the students, and there we also usually take on either a bachelor or a master student each year. And it's very much, again, something that has to have, if we're paying them for it, it's something that has to have some type of contribution to the group. But I think it's great. I think getting bachelor students involved in projects is really, really cool. Of course, we need to be aware of the fact that they are early career researchers. They're still very much trainees, but it is a chance for them to get some hands-on research experience, and usually it's a chance for us to advance in a project that just needs somebody to sit down and think about it for a while. So yeah, I'm answering the question here by Paul. My screen is just frozen. Where was the question? There was a question here. Do undergrads ever have the chance to get involved in the work you do? Yes, either via their bachelor thesis or with summer internships. And often people will put a list of projects, especially for the bachelor thesis, and then the students pick a topic and then they contact us. But what happens sometimes is we get students reaching out proactively that just email us like, hey, is there any chance I could do a project with you this summer? And I love it when that happens, because that type of proactiveness is like, this person is really interested in what we're doing. I don't have to go out and hunt for somebody to come and work with me. They want to come work with me. And it's very, very cool when that happens. So yes, there are undergrads involved in what we do, and I think that's very cool, and I love working with undergrads. As students progress more in their career, they get more opportunities to get involved in research. But also, I think I know people who did their bachelor thesis in cosmology and then didn't continue to do a master's, and that's perfectly fine. So the bachelor thesis really is, or these summer internships really are just like, here's what a research group looks like. And if done properly, it's really the place to ideally show the students the goods and the bads of the research that we do, and why they should potentially join us for a master thesis and then maybe a PhD if there's funding. So yes, undergrads do have the chance to get involved, and it is super cool when that happens. And I love working with students in general. To follow up from Paul, you're encouraging your third-year daughter to email a bunch of profs asking how she can get involved, even just as a volunteer. Yes, strongly encourage doing that. There will be a lot of professors who won't answer because they're going to get a lot of these emails, and there will be some professors who will never answer. But I would absolutely advise your daughter to do this, or anyone to do this. If you're in your undergrad, whatever the topic, just email people, be like, hey, can I just join a group meeting? Can I just come and listen to what you're doing? I can just be there if you need somebody to derive an equation or to stare at a code for an hour. Absolutely, being proactive, emailing professors is a good way to do this, but don't always expect an answer, because professors are going to be extremely busy. I think it's especially good if the professor already knows you in advance. Like if I get an email from someone I've never heard of, like, can I come work with you? It's going to be a bit harder for me to know what I'm basing that on. Whereas if it's someone that I remember, for an example, from one of my courses, or a student might message me like, hey, I took I saw you in this course. Can we follow up on that? It just provides this connection that makes it a bit easier to establish this working relationship. So absolutely, cold email professors. Don't always expect an answer. That's going to happen. But I would say, especially if it's professors that you've had an opportunity to chat to in lectures or in a teaching environment, then you're more likely to get a positive response. And I feel like this is not just an academia thing, that in general, just if you know people, they're more likely to be friendly with you. And in general, just emailing people is a good way of showing that you're proactive about something. So yes, absolutely a very, very good thing to do, I would say. So I saw there were several questions, and I think several cool questions. So let me just go back. There was one that I saw by John. What do you think about the river model of space-time? I'm trying to think of what the river model of space-time is, and I cannot remember what it is. I've definitely heard that before, but I can't remember exactly what the idea is behind the river space-time. River Space-Time just makes me think of River Song from Doctor Who, which I'm guessing is not the model in question here. So, sorry, John, I'm not completely sure what the river model of space-time is. If you can put a short summary, like a 2-line summary, just so I can remember what your question is about, then I can try to answer. But right now, I'm blanking on what the river model of space-time is. Guessing it's like space-time flows like a river, but yeah, I'm missing. I cannot comment on that right now because I don't know what I'm commenting on. It's somewhere in the back of my brain, but not in a place where I feel like I can answer that right now, I'm afraid. Okay, there was a comment from Scott. When they say bigger black holes are less dense, they're talking about the event horizons. I get the square cube rule, of course, but I heard that a black hole the size of the observable universe would have the density of air, and that just sounds wrong. Fun fact, a black hole the size of the observable universe would have the same density that the universe has. So if you take all of the matter that we have in the universe and you ask the question of how big would a black hole be containing this amount of mass, the answer you get is the size of the universe, which is very cool. Basically, the event horizon of a black hole is very similar to the event horizon that we can imagine beyond the observable universe. So that is pretty cool to think about. Now, the thing is, the size of a black hole is determined by its Schwarzschild radius. This is the event horizon. We call it the Schwarzschild. I pronounce that two different ways. It's a German name. It's Schwarzschild. The Schwarzschild radius came out full German. Yeah, the Schwarzschild radius is the size of the event horizon. So a black hole is a region of space-time that is so dense that nothing can escape, not even light. You need to travel faster than light in a vacuum to escape a black hole. As far as we know, nothing can travel faster than light in a vacuum, and therefore nothing can escape the gravitational pull of a black hole. However, however there, nothing can escape the gravitational pull of a black hole. And the event horizon is the region, the kind of point of no return around a black hole. So before you reach the event horizon, you can still escape. Once you pass the event horizon, the gravitational pull is so intense and nothing can escape. So the event horizon gives us the size of the black hole. Now, in terms of the density, it gets a bit more complicated because we know that, it's going to be a sphere. We know its volume. We know the radius, but the way we calculate the radius of a black hole depends proportionately on its mass. So when we calculate the density, it doesn't scale directly the way a normal sphere does, where you have the radius cubed. In this case, you actually can have that the bigger the black hole is, the less dense it is. This is somewhat counterintuitive, but you can have black holes that are very, very big and not very dense. So it's a bit confusing because I just did the same. I said a black hole is a region of space-time that is so dense that nothing can escape. That is actually not completely correct. What we really mean is a black hole is a region of space-time that has such a strong gravitational pull that nothing can escape. And we can think about it when we're talking about black holes the size of the sun. Using density is a good metric. They are ridiculously dense. But when you go to something like a supermassive black hole, a supermassive black hole would hypothetically float on water because it's less dense. So yes, you can, because the radius is proportional to the mass of the black hole. The bigger the mass, the bigger the radius. And we know that density is going to be mass over volume. Volume is R3. So you get the thing that the density doesn't increase directly with increasing the size of the black holes, which is pretty cool. So you can actually have black holes that are really, really big, but less dense than, for an example, water. So that is absolutely possible. But always when we're talking about the size of a black hole, we're referring to the event horizon, the size of the event horizon. I've realized, Scott, I'm not completely sure what your question was, but I hope I've answered it. If not, please do follow up with that. But yes, you can have black holes that are very, very big, but not very dense. And see if there's some follow-ups before I go back to what I was just to the next questions. There's a comment from Press here saying, our universe is the singularity of a black hole. Yes and no. So there is this is actually one of my favorite questions to ever come out of my live streams back in the Periscope days. I know some of you remember the Periscope days. So back in the Periscope days, someone asked me the question of, if you take all of the mass of the observable universe and you condense it to a black hole, what is the size of the event horizon? So I calculated it after that stream and I got the answer of the size of the observable universe. This confused me. I went to my PhD advisor and was like, can you redo this calculation? We did this calculation together and we pulled out the same answer. And it's very curious that if you take the observable universe, you take all of the mass in the observable universe, it does have the right mass radius to be a black hole. Now, as this was just as Press just pointed out here, are we saying that the universe is a black hole here? No. What we are saying is that all of this relies on the assumption of the universe being flat, which is what we have measured. Once we have a flat universe, we define a flat universe as a universe that has the critical density to make it flat. Helpful, I know. Critical density is the density the universe needs to be flat, and if you're over that, you're going to be closed. If you're under that, it's going to be an open universe. And when we construct this idea of the universe has to be spatially flat, which matches our observations, then you pull out that our universe behaves like a black hole. Now, this does not mean that we are inside a black hole. It just means that if we consider a black hole as the limit beyond which the gravitational pull is too strong for light to escape, and then we consider that we define the limit of the observable universe as the distance that light has been able to travel given the finite lifetime of the universe, it kind of makes sense that both of these are really like limiting factors on what light can do. So it does actually make sense that they are connected. This doesn't necessarily mean that the universe is a singularity. It just means that we have the same density that a black hole of this mass would have as well. That the same density, the same radius. So the universe shares very similar properties to what we call black holes, but this is just based on how we've constructed general relativity and the assumption of the universe being flat. Okay, sticking with black holes because there's a few follow-ups, and then I know there are other questions to answer. A few follow-ups here. One there we okay. Directly one from Pythagoras, but is the curved space-time in a black hole significantly non-Euclidean? It's quite hard to describe anything inside a black hole because inside a black hole our equations break down. Now, when we talk about singularities, it's a fancy way of saying our equations break down. Now, we know, according to Einstein's general relativity, that mass bends space-time, the curvature of space-time tells objects how to move. So you have this space-time that can, and gravity can be interpreted as the curvature of space-time. Once you reach inside a black hole, the curvature basically becomes infinitely big. And this is why we call it a singularity, because it basically means that our equations break down. And the curvature of space-time becomes so much that you usually get those pretty diagrams that people do where, you know, if you have space-time, and I'm drawing a picture here, I'll show you in a minute. We often draw space-time as something like this here that curves, and when you put a black hole here, it curves so much that it never joins again at the bottom, and you have this, which would hypothetically be the opening of a wormhole. So this here is where it becomes quite hard. Like, how do we define this curvature when it is infinitely big? How do we define the curvature inside a black hole? And this is what we mean when we say it's a singularity. Singularity is a fancy way of saying our equation stopped working. So I think it's a great question. Is the curvature of space-time in a black hole significantly non-Euclidean? The curvature inside a black hole is infinite. Does that make it non-Euclidean? Good luck doing the math on that. The equations just really break down because it's such a strong gravitational pull that when we interpret gravity as being the curvature of space-time, we cannot describe it inside a black hole. This is the singularity. If you were to throw yourself inside the event horizon of a black hole, you would not notice that you've gone into the event horizon. There's no physical thing where you say there's a barrier or there's a threshold or there's a point of no return sign. But mathematically, at that point, you cannot come back. You'd need to travel faster than light to come back. And mathematically, at that point, we can no longer explain what is happening to you. So please don't jump inside black holes. It is probably not a good thing to do. Although, maybe you find a bookcase. We don't know. But yes, we don't know what happens inside a black hole. Sticking with the black holes, there's a question from Gredov here. Does a spinning black hole bulge in the middle, i.e. are they circular or elliptical? Yes, they are. Yes and no. So most black holes do actually have some amount of spin, just because everything in the universe has a bit of spin. The reason for this is as long as you have the slightest amount of spin in the universe, you will keep spinning. So in order to have something with absolutely no spin, you need to just happen to create an object that has no spin. And of all the possible spins to have, 0 is a special. It's not any special than any other number, but it's just as unlikely as any other value of the spin. So saying that you want an object to not spin is quite unlikely. So most black holes do spin. As far as we know, all black holes actually spin. Now, when you have a spinning black hole, you do have some conservation of energy here that is going to keep it being approximately spherical. You have the angular momentum here, but you are going to keep things kind of being pulled inwards from every direction. So even though it's spinning, it doesn't tend to have too much of a bulge. However, if it spanned a lot, then you would have a slight kind of flattening at the pole. So if you imagine this is my black hole, I have a black hole plushie at hand. If I'm spinning the black hole on this axis, so like this, it is gradually going to get slightly squashed and slightly elongated. And then you can have the fun thing that if you have two black holes together orbiting around each other, the event horizon actually becomes kind of a torus, like a donut, because they've been flattened out, and then you have this kind of donut thing as they're spinning around each other. So a spinning black hole, the faster it gets, it would get slightly flatter, but you really need to spin quickly for this to happen because the gravitational force is going to do a pretty good job of keeping it spherical. Once you start spinning it, you need to spin it quite quickly, but then you can gradually start flattening it a bit. However, black holes are really, really, really big, generally speaking. They could be small, but the ones we've seen so far are big. And in order that you don't have really a noticeable difference, it's just like the Earth is slightly squashed at the poles because of its rotation, but it's not overall noticeable, and it is fair to describe the Earth as a ball. Same for black holes, unless this either spinning very quickly or you have multiple black holes. And then the event horizon can deform and no longer be a sphere. So that is a very cool question. Feel like, okay, sticking with black holes again, I know there are some other questions here. There was a question about programming. There's a follow-up to the river model, but sticking with black holes, and then I will go back to the other ones. We have a comment from Paul here. Crazy thought. I love crazy thoughts. Huge non-dense supermassive black hole might have uneven distribution of matter inside, so maybe planets and other things. Anything but a library. Yes. So how would you go about having an uneven distribution of matter inside a supermassive black hole? So let's ignore the fact that we don't know how to describe the inside of a black hole. If you can imagine, gravity is pulling in every direction to the center. Everything is being pulled to the center of mass, which is at the center of this black hole. Then it would kind of make sense for it to be uniformly distributed. The density profile of the black hole should be pretty uniform. But we don't know that exactly because, again, we cannot model what is happening inside a black hole. So you could have patchy chunks. I think just based on how usually gravity pulls things around in a symmetrical way, there is a reason to think that the distribution of mass inside a black hole would be approximately symmetrical. However, we really can't describe what is happening inside a black hole. There's also the question of what happens to all the information that goes into a black hole. Where is that stored? So there are a lot of things you can do, a lot of questions to be asked with black holes. And unfortunately, anything that involves what is happening inside the black hole is a question we can't really answer because our equations stop working inside the black hole. Okay, we have a comment here from Lethargo. Avoid quicksand, multi-level marketing schemes, and black holes. Yeah, I feel like that is overall good life advice. You know, avoid quicksand. Although, to be fair, I think quicksand has turned out to be a much less significant problem in my life than TV series and movies led me to believe. You know, as a kid, I was like, I'm going to find quicksand every day. I need to know how to get out of quicksand. I have not once in my life seen quicksand. So that is one of those things that was potentially hyped up a bit more than it needed to be. But in general, avoid quicksand, avoid fire swamps, avoid multi-level marketing scheme, avoid the black hole, jumping into black holes. That is overall good life advice. Okay, sticking with black holes because we have a lot of follow-up questions to black holes. I know there are other questions to go back to. We have a question from John here. Do you think direct collapse black holes were possible in the early universe? I love this question. So when we think about black holes, we often think about stars that have reached the end of their lifetime and collapse to form a black hole. However, there's another type of black hole which is known as primordial black holes. Now, primordial black holes would be black holes that are formed in the very early universe when regions of space-time are so dense they can directly collapse to form a black hole without going through the whole stellar evolution phase. So in the early universe, we know we had quantum fluctuations, which leads to density fluctuations. This just means there are regions of the universe that had slightly more dense, space-time itself was slightly more dense, and regions that were slightly less dense. How do we know this? I'm so glad you asked. We know this thanks to, among other things, the cosmic microwave background radiation, the CMB. This here is the oldest light in the universe. This is a snapshot of what the universe looked like 380,000 years after the Big Bang. Got it before the half-an-hour mark. And what you can see here are background photons, or particles of light. We have some that are a bit more orange and some that are a bit more blue. These are ones that have a bit more energy and ones that have a bit less energy. And we know that the regions that have more energy, the regions that have less energy, is related to regions of space-time that had more or less density. So we could use this cosmic microwave background radiation to study what the universe looked like 380,000 years ago. This gives us a huge amount of information. But one thing that it tells us here, among many other things, one of the things it tells us is that in the early universe, there were patches that were more dense and patches that were less dense. I hope you all appreciate that I just managed to squeeze in CMB while talking about primordial black holes. So thanks to things like the CMB, the cosmic microwave background radiation, we know that the universe had regions that were more dense and regions that were less dense. So the question is, were these regions dense enough to form a primordial black hole? And this is a matter of ongoing, this is something that is still being researched. It's an ongoing debate. There's a lot of work being done on primordial black holes, because if primordial black holes exist, they could account for a bit of the dark matter. So we know that the universe has three main components: everything we see, everything we're accustomed to, everything from me to my cold tea to my black hole plushie. All of this is normal matter. Normal matter only accounts for 5% of the energy budget of the observable universe. There is another 26% that is in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally, but doesn't interact electromagnetically. So we cannot see dark matter. As far as light is concerned, dark matter is not there. Dark matter is invisible. The remaining 69% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that is pretty much everything we know about dark energy. But there is a big question: what is this 26.2% in the form of dark matter? And one possible answer is primordial black holes. So going back to the question, that I am actually answering a question here, I just took a few tangents along the way. Do you think direct collapse black holes were possible in the early universe? Yes, but we have not found them yet. However, we don't have clear evidence saying that we have found them yet, but if they exist, they could account for some of the dark matter, or even all of the dark matter, depending on who you ask. There is a very cool thing that primordial black holes is something that we might be able to find using gravitational waves, which are ripples in the fabric of space-time. I mentioned it briefly last week as well. There's a space mission that is set to launch in about 12 years, which is called LISA. LISA is the Laser Interferometer Space Antenna. It is a gravitational wave observatory that is launching to space and it's going to use lasers to try to measure tiny vibrations in the background of the cosmos, which is ridiculous and amazing. And if we find these tiny gravitational waves, depending on what they look like, it could tell us if primordial black holes are real or not. So, do I personally think that direct collapse black holes were possible in the early universe? Yes. Have we found any to date? Probably not, although there are people who say we might have done. Are we going to find them in the future? I think so. I think if primordial black holes exist, LISA will tell us if they're there or not, and will also tell us if they make up the dark matter or not. So, out of breath after that. Yes, primordial black holes are a possibility, where we just have a region of the universe that collapses to form a black hole without going through the whole stellar evolution phase. We have not yet found them, but there is hope that we will in the future. Okay. Managed to throw CMB at you there while talking about primordial black holes. Just had to do that. For anyone who's new here, there's the ongoing thing of, can I do a whole stream without showing that picture? The answer is no. It took me almost 30 minutes today, but you got your CMB at some point. Okay, more questions. The questions are coming quicker than I can answer them. Let's go back. There's just a follow-up here to primordial black holes, or several follow-ups to primordial black holes, and then we can go on to the other questions here. Okay, where were we talking about Hawking radiation? Just want to say there's a comment here from Abyss. Hey Abyss, great to see you, by the way. Curved black holes can have a toroidal volume called ergosphere that appears to be metastable space. Yes, so if you have a curved black hole is a black hole that is rotating really quickly, and you can form this torus if it is rotating quick enough. And that is a very cool phenomena and a very fun thing to think about. Okay, sticking with primordial black holes, then we're going to go back to normal black holes and then to the other questions. Question from Prath here asked a few minutes ago, if matter was able to collapse into primordial black holes, why didn't all of it collapse into one black hole right after the Big Bang? So here's the cool thing. When we're talking about primordial black holes collapsing, it is not matter that is collapsing, it is space-time itself. So primordial black holes would form before the first atoms, before the first elements, before we can talk about anything more than just protons and not even protons, just quarks. So primordial black holes, if they exist, were formed really in the infancy of the universe. And it's just when space-time itself collapses. So it's not about having a huge amount of mass in one region, it's about space-time itself collapsing. So the question of why didn't this happen everywhere, the answer comes back to the idea that we had these small differences. So one thing the way we generally describe cosmology is a background level and then the small changes on top of this background. So I'm just going to draw kind of a bumpy line here. Okay. So imagine this is what the early universe looked like. A patch of the early universe shown on a piece of paper. And you can see it all has, it's approximately the same, but then there are these tiny differences. There's tiny hills and tiny valleys here. This is what we call the perturbations on the background, or the vibrations, the tiny differences on the background. So when we're talking about the early universe, we're not saying, I'm going to get a new piece of paper here. We're not saying that the whole thing was like this, right? This is a place where you can have a lot of stuff happening. What we're saying is the universe really just had these tiny differences. It's still approximately the same scales, like tiny differences. And this is what we call the perturbations on the background. Now, the idea behind primordial black holes is that, for an example, this valley here could form a primordial black hole. But just because this forms a primordial black hole doesn't mean everything is going to be dragged into it. Now, we know that gravity is the weakest of the forces. The further away you are from an object, the less you feel the gravitational force. So even if you form a primordial black hole here, this is not going to affect other regions of the universe. So you can have primordial black holes forming in some places, kind of in these valleys, while leaving the rest unaffected. This is why a lot of cosmology relies on what we call perturbation theory, which is explaining these tiny differences on top of a background level. So you can have regions of the universe that collapse into primordial black holes without that affecting the rest of the universe. Perturbation theory is also what we need to explain the cosmic microwave background radiation, this amazing thing here. So again, the tiny temperature differences that you get here are perturbations, temperature perturbations. And this is why actually unpacking this, there's a whole course we normally take called perturbation theory, which is where the CMB comes from. And it ties into primordial black holes and basically why there are galaxies in the universe. Which was incidentally my favorite course and the main topic of my PhD thesis. My PhD thesis was like perturbation theory. And I wrote a really nice introduction to perturbation theory in my PhD thesis, incidentally. I'm very proud of that. Okay, keeping with primordial black holes, and I know there are still more questions to come. If primordial black holes have, follow up by Prath, if primordial black holes have been around for 13 billion years, and why haven't they grown into supermassive black holes? Excellent question. And in fact, a supermassive black hole is a black hole that is billions of times the mass of the sun. We believe there are supermassive black holes at the center of every galaxy. Now, the question is, where did supermassive black holes come from? We don't actually know where supermassive black holes came from, because we know how to form normal-sized stars. We have ideas on how we could form primordial black holes, but how do we actually form supermassive black holes? And this is something that we really don't know, because it's quite hard to explain how we form primordial black holes. There's how we form supermassive black holes. There's a few different ideas, but how did black holes become so massive? How did they become billions of times the mass of the sun? And one idea behind the origin of supermassive black holes is actually primordial black holes. So could it be that these primordial black holes in the early universe merged at some point, smashed together? This happened multiple times, and they started getting matter falling on top of them. They gradually grew. So could the supermassive black holes that we see today be explained by primordial black holes? In this case, you could have both supermassive black holes and primordial black holes coexisting today by the fact that you need primordial black holes to be close enough to each other in order to merge and grow into the supermassive black holes. So it's an excellent question, Prath, of why have primordial black holes not turned into supermassive black holes? Who's to say they haven't? So if primordial black holes exist, they might give us an explanation for supermassive black holes. So kind of cool, like primordial black holes do everything for you. They could explain dark matter, they could explain supermassive black holes. There's something that could happen naturally in the early universe, which is why supermassive black holes why a lot of people like supermassive black holes. So they could have started as tiny black holes that then formed into supermassive black holes. So that's a very, very, very cool question. Okay, comment from Anne saying, I have not shown the CMB. I did. You missed my very cool segue of showing the CMB while talking about primordial black holes at the 29-minute mark. I came up with a very clever way to flash the CMB. I'm quite proud of that one today. Normal black holes, yeah, normal black holes as opposed to primordial black holes. Okay. More questions. Let me just glance through it here. The CMB looks like a star. The CMB is very pretty. The CMB is very, very cool. Okay, sticking with primordial black holes. How large was the universe when they formed? Infinitely big, but a lot smaller than it is now. We're talking about primordial black holes forming basically at the end of inflation. So if we think about the history of the universe, there is this period of exponential expansion initially that is called inflation. I'm just bringing up my my history of the universe picture here. We're not going to talk about what it looks like. Second one, this one here. So you see there is this initial stage where we have cosmic inflation. So if primordial black holes were formed, they were formed after inflation. So the universe has already grown exponentially at this point, but substantially smaller than what it is today. So then we could hypothetically have primordial black holes forming at the end of inflation. Then when we talk about the formation rate, what we always talk about is how many black holes could form in every Hubble patch of the universe. So a Hubble patch is just the size of the observable universe at a given time. The Hubble radius today coincides with the observable universe if we neglect dark energy and accelerated expansion. So when we talk about primordial black holes, we talk about how many can form in each Hubble horizon. And then depending on how you go about forming them, which model do you use, which underlying ideas. I've never not shown the CMB. That is a fair statement. I read it as you've not yet shown the CMB. Yes, I have never not shown the CMB. Yes. So then depending on what formation mechanism you choose when you simulate primordial black holes, you either don't get any, you get one in every patch of the universe, or you get enough to explain why we have supermassive black holes today. So yes, so inflation was too high to let primordial black holes form. I'm not sure what you mean by too high, but generally it's considered that primordial black holes would form once inflation is finished. Inflation finishes and then you form primordial black holes. Or often people look at an idea where inflation itself is what generates the primordial black holes. So when you go through this phase of inflation, you have some kind of residual energy that can then be turned into these primordial black holes. So generally when you study primordial black holes, it often goes hand in hand with studying inflation, because we're talking about very similar epochs of cosmic evolution. So they're things that we're talking about forming or appearing at the same approximate time. So you can have models of inflation that predict primordial black holes. There's also models of inflation that do not predict that specifically forbid primordial black holes. So then, if we don't find primordial black holes, or if we do find them, we can also say things about different inflationary models. Usually primordial black hole talks or seminars that I go to start with, here's what primordial black holes can do for you. And it's a long list of cool things that primordial black holes can do. It's like, do you want to know what dark matter is? Do you want to know what supermassive black holes are? Do you want to know how inflation worked? Maybe primordial black holes can answer at least one or two of these questions. Or maybe not. Following on with primordial black holes and supermassive black holes, there was a question from John a while ago. Do you think that very early supermassive black holes JWST has found could have come from primordial black holes? It could be. So JWST, the NASA mission that launched 3 years ago by now, has found some supermassive black holes that seems to be younger than or older than what we expected, so formed in the very early universe. And these could be related to primordial black holes. In fact, there were papers of has JWST seen primordial black holes? Maybe not. We need more data to answer that question, but it is an excellent question, and it is very much a thought pattern that people have had of, given that we found these supermassive black holes that seem to have formed before we had actual stars, or do they have primordial origin? Are they primordial black holes that then became supermassive black holes? So this is an excellent question, and it's something that we need more data to answer, but there are definitely people working on that. Follow-up from Prathia about primordial black holes and inflation, like space itself was expanding too quickly to let the mass in it collapse into a black hole. Yes. Yes, if you think that during inflation, space-time is being stretched, it's quite hard for something to collapse during inflation when you have all the space-time stretching. But at the end of inflation, this is also the cool thing, that if we, where's my sketch? Right, when we have our little bumpy universe down here, it was probably even, but so before inflation, the idea is these bumps were just quantum vibrations, and inflation stretched these quantum fluctuations so much that they then became the perturbations in the universe. So these ups and downs that give us the CMB, which is really cool because you can tell a story going from inflation through the CMB to the galaxies that we see today via this whole perturbation theory. It really ties everything together, which is why it's one of my favorite topics. Okay, I think I've answered all of the black hole questions. Let me just very quickly check the black hole questions, and then we'll go back to the other questions that were asked at some point very early on as well that were not black hole related. Okay, I'm pretty sure I answered all of those questions. If I have not answered a question about black holes that you asked, please feel free to ask that one again and I will try to answer it. But I think I've answered all of the follow-ups to the black holes. So let's take it back to the top and go through all the comments again, because there were some that I have not yet answered. And it would be good if I could put a marker on comments of like, come back to this one, but I can't. So I have to just go and glance through all the comments again. But that gives me a chance to catch my breath. Okay, so there was the question quite early on about the river space-time, and I asked for clarification. So John followed up with, I heard someone talking about space-time flowing towards a mass instead of curving around it. Huh. I'm not familiar with that idea, to be honest. It does. So space-time would be flowing towards a mass. Yeah, I would then ask the follow-up question to that of why would space-time travel towards a mass or bend towards a mass? What is causing that? Because in our current picture of space-time, in Einstein's general relativity, we have space-time. Gravity is the curvature of space-time, which is caused by objects with mass. So space-time bends around objects with mass. I'm not sure how you would construct a model where space-time is kind of falling into the mass or chasing a mass. I'll look into that. I've made a note of river space-time, and I will look into that because it sounds like an interesting model to read up about. So yeah, I'll read up on that. That sounds very cool. Thank you for that question. I'm sorry I don't have an answer right now. There was a question at some point very early on. Where was that question? By Prath. What percentage of your day-to-day work is programming? That very much depends on my day-to-day work, but I would say on a good week about 50%. On a bad week, maybe, or bad coding-wise, maybe 10%. So I'm a computational cosmologist. I do scientific computing, which means a lot of what I do is developing the codes to answer these questions. You know, when I show you pictures of the CMB, for an example, which is currently not the image I have loaded up, but when I show you pictures, for an example, of the cosmic microwave background radiation, this comes from somewhere. This is not the actual data that we took, or this is the data, but then how do we match this data onto a model? And for this, we need to run computing codes. We need to run cosmological simulations. I develop codes that allow us to do cosmology, that allow us to do early universe cosmology. I currently develop 3 main codes that are publicly available and that I contribute to, but then I also have my own versions of these codes, and for each project we need different versions of the codes. I would say all of the projects, all of my publications have involved some level of coding. What often happens is we build the code, which is where I will spend a week where I'm basically coding, and then we do the tests, where we wait for results and work on other things, think about ideas, think about how we're going to code the next thing. And then when we get results, we go to the bug fixing phase because the results never work the first time. And then a lot of the coding becomes bug fixing. So there's always this back and forth of, okay, now I'm doing research, more research focus, now I'm doing more coding focus, and it goes back and forth. So I would say on average, probably over the year, about 1 or 2 days a week out of my 5-day work week are spent coding. But it comes and goes. There are some weeks where I'm literally just coding, and there are some times when I don't touch codes in a while. Right now, I'm at the stage where I just put out a paper quite recently, which I'm really happy about. And now I'm jumping into another project, which means when I go back to work tomorrow, my first task is a coding task. I kind of imagine that this coming week, especially because July in Finland is a big holiday. There's probably going to be like 2 other people in my entire office, which means no meetings, no seminars, no student meetings. All of my students are on holiday. So the whole week, I'm basically going to be coding. That is exciting and also a bit like, whole week of coding. So yeah, it very much depends on the week and how the projects are going. But I would say on average, I spend probably 2 days a week out of my 5 coding. Okay, more black hole comments and questions. And then there were other questions. There was one about the large scale structure earlier, like Guadav, that I need to go back to. There's one about baryon acoustic oscillations I need to go back to, but more black hole questions. Question from Paul here. If inflation prevented black holes from forming, would future big rip dark energy also rip apart black holes or change event horizons? Yeah, so it gets very cool when we start thinking about that, right? Because so the idea of dark energy is driving the accelerated expansion of the universe. There was the idea that depending on the strength of dark energy, this acceleration could increase in the future. We know that it's accelerating. The universe is expanding faster today than it was in the past. If this trend continues, the question is how fast is this acceleration going to get? Will it be enough to rip everything apart at the atomic level? Now, if it reaches the point where the gravitational force is strong enough to pull apart atoms, to rip apart protons and neutrons and just scatter all of the atoms throughout the universe, when the universe turns into this basically nothing, everything just gets torn apart, nothing exists anymore, what happens to black holes? And that is a cool question. If so, gravity is the weakest force. We know that black holes are held together through the force of gravity. If we're talking about a big rip scenario that is so intense that it can overcome the strong force, it can definitely overcome the gravitational force. So in fact, black hole, it's probably going to be, galaxies start being flung apart. Then you get planets and stars flung apart, black holes, and eventually you reach the point where atoms themselves get ripped apart. So yes, we can have black holes being ripped apart by the expansion of the universe in the future. Okay, recommendation from Abyss to watch 60 Symbols after this stream. I've not seen it. I trust Abyss. Go watch it. If Abyss says it's a good recommendation, probably is. Okay, comment from Perth. I had more of a black hole comment than a black hole question up there. Black hole comment, not a black hole question. Yeah, we talked about space itself expanding too quickly, so matter couldn't expand. I often do the thing where if a comment doesn't have a question mark at the end, I kind of ignore it and don't answer it. But Perth, I'm not sure which question of yours I didn't answer because I feel like there was the Hawking radiation one, but otherwise I think okay, yes, there were a couple of black hole questions I missed. Sticking with black holes here, so yes, we had a comment here by Perth. If black holes are what light can't escape from and white holes are what light can't fall into, then everything else in the universe is a grey hole. Sounds about right. There are shades of grey in the universe, probably more than 50 of them. Okay, I see people complaining about how exaggerated topography and quicksand were, and I agree. So, if black holes have Hawking radiation, then do white holes have Hawking absorption? Excellent question. So, Hawking evaporation is the idea. We know that nothing can escape the event horizon of a black hole. However, what you can do, what the universe likes doing frequently, is producing particles from kind of nothing. So the universe has this background energy, and sometimes you can kind of borrow energy from the universe to produce a particle and an antiparticle. These immediately annihilate and go back into the universe. However, if you produce a particle and an antiparticle right on the event horizon of a black hole, what can happen is you produce the particle, the antiparticle, one falls in, and it kind of you've borrowed energy from the universe. In order to give this back, the black hole will lose a bit of mass and one of the particles escapes. So we are not saying that a particle escapes from the center of a black hole, but rather a particle is produced on the event horizon and goes outwards. One falls in, one goes out, the black hole loses a bit of mass. Now, a white hole is the theoretical counterpart to a black hole. So if I have a black hole, a white hole is its theoretical counterpart. The idea of a white hole is it repels everything. Now, white holes haven't been shown to exist. They are something that is a mathematical object, like mathematically, we should have a symmetrical version of a black hole. So if a black hole is pulling things in, a white hole is pushing them out. So what happens to Hawking evaporation? Now, I would imagine here, if you have things being pushed outwards at the event horizon of a white hole, you wouldn't be able to have one particle falling in and one escaping, or would you? I'm not sure. I've never thought about Hawking evaporation or Hawking absorption on a white hole before. That is a cool question that I'm not completely sure how to answer, because we're talking about Hawking evaporation that has never been proven on top of white holes that are a hypothetical construct. I'm not sure. It would make sense that if we're talking about a white hole being kind of the symmetrical opposite of a black hole, if a black hole can have Hawking evaporation, emitting something, then a white hole would have the opposite, where it does absorb a particle. So it makes sense, but I'm not completely sure. I'd have to look at it. But yeah, that is a very cool idea, to think about a white hole having kind of inverse Hawking radiation. I like that idea. Okay, my tea is very cold by now. Back to questions. Let's see if there are more black hole questions. And if there are no more black hole questions, then I can go on to the other questions that are still there. There's ideas about watching the Kurzgesagt videos of black holes. Absolutely recommend Kurzgesagt. Their channel is great. Their videos are always cool. Yes, thank you, Press, for copying the comment about grey holes. I'd already scrolled up and found it, but thank you for copying that. Comment from Abyss: you should do a stream on the exasperating nature of publishing. Yeah, that is coming soon, actually. Not just publishing. At some point soon-ish, I'm going to do a stream called The Ups and Downs of Academia. And it is going to be a rant, and I can assure you I will talk about how academic publishing works. And I will also talk about how grant proposals work and how things do and don't work in academia. That is going to be a fun stream that is coming at some point soon, when I'm in a position where I can actually do that stream in a reasonable way. Okay, yes. Okay, I see I scrolled back to find the questions. I'm pressing posted both of them. Thank you for doing that. And now I've scrolled down and seen your comment saying you don't need to scroll back up. Already did it, but thank you. I do appreciate you copying it there. Okay, so do you think vacuum energy is likely to be dark energy? So going back to this idea that I was talking about, that the universe has this background energy that can be used to kind of produce particles that then evaporate back into the universe. Is this the same as dark energy, which is a background energy that feels space-time? It could be. However, there is the problem that if we calculate the kind of average energy of the background of the universe, and if we calculate the average energy of dark energy, there are many, as in 127 orders of magnitude difference between these values. So there are models of dark energy where dark energy is related or very similar to the vacuum expectation energy of the universe. The problem is the energy scales are very different, and it's quite hard to explain this. This is something that is known as the hierarchy problem. We have many hierarchy problems in a lot of things, but also in cosmology. And one of them is related to this energy problem. So it is possible that the vacuum energy could be related to dark energy, but it is quite hard to to map those together. Yeah, coming from Abyss here, no idea on white holes and Hawking evaporation. We need to break the math to see if white holes absorb radiation, but from information conservation point of view, they might do, they might not do. Yeah. Hey, David Dunn, thanks for stopping by for a small time. Great to see you, and hello and goodbye. Okay, we are 1 hour in, but there are at least 2 very good questions I have not yet answered. So I'm going to take it all from the top one last time, and I'm going to make sure I have answered every question. That is always my mission on these streams. I never used to be able to do it in the Periscope days. There were too many, and they disappeared. But now that I have infinite scroll and I can scroll back, the plan is to answer all of the questions. So I know there was a question quite early on about large-scale structure that I want to go back to. We talked about programming. Then there was a question from Guadav about 45 minutes ago by now. How do cosmologists map the large-scale structure of the universe, and what have these maps revealed about the distribution of galaxies and dark matter? I love this question. This is an excellent question. Rather than give a full answer, I'm going to recommend that you go and watch the stream I did recently called the first DESI results. So DESI is something known as a dark energy spectroscopic instrument, and it is one of the instruments that we have that is currently giving us the most detailed map of the matter distribution in the universe. It is a very, very, very cool map. So how do we map the large-scale structure of the universe? We build very, very good telescopes that go out and take a lot of photos. I actually have it here. Okay, so we build telescopes that go out to space or ground-based and take a lot of photos. We use 2 things. We use the amount of light we're receiving, and we use how much that light is redshifted. So we know that light is a wave. When it travels away from you, it gets stretched. When it travels towards you, it condenses, it gets compressed. This happens in the universe due to the expansion of the universe. Things travel away from you, they get redshifted. When things travel towards you, they get blue shifted. So we can use both the redshift and the amount of light we're getting from objects to measure both their distance and the speed at which they're moving away from us. This allows us to build 3D maps of what the universe is looking like, so what the large-scale structure of the universe looks like. Meanwhile, we can also do simulations on our computers where we put everything we know about matter, about dark matter, about how particles behave, and we see what comes out. If we do the simulations on the computer, we get something like this. This is the most up-to-date simulation. This is known as Flamingo. You might have seen previous versions of this image called the Illustris simulation and the Millennium simulation. Flamingo is the updated version. What you can see here, every glowing dot represents a galaxy. This is a simulation of what we expect the universe to look like on large scales once we factor in how dark matter behaves, how gas behaves. So this here is a simulation. Then we can use telescopes to map this. Up until recently, one of the best tools we had was what is known as a Sloan Digital Sky Survey. The Sloan Digital Sky Survey gave us this data here. Again, every dot is a galaxy. This is actual data. And you can really see here that we are recovering this cosmic web that we saw in the simulations. So the data from the Sloan Digital Sky Survey is giving us a really good map of what it's really matching our simulations, our predictions. So we simulated this cosmic web, and this is what we are observing. But now we have DESI, Dark Energy Spectroscopic Instrument, which is a telescope in Chile, and it is mapping galaxies up to a few billion light years away. It is planned to run for 6 years. It has already run for 3. We have the first data release of the first 1 year of data, and they have already mapped 6 million galaxies in the first year. And you've probably seen it by now because I show it very frequently. This here is what the DESI results look like. You can see in the background there's this amazing image, and then the close-up. There is really a huge amount of data here. Every glowing dot here is a galaxy. This is amazing. This is the most detailed map we have of matter in the universe by DESI. I did a whole stream about this a couple of weeks ago. Really, go watch it. I had a lot of fun in that stream, and I go through every detail about this image and its implications. So how do cosmologists map large-scale structure of the universe? We build big telescopes. What has this showed us? It's given us this. What does this told us about dark matter? We're working on that. That's the one we're going to answer soon. But the DESI results did have hints that maybe dark energy doesn't behave the way we expected. But yeah, that is the short version. If you want the full version of the answer to your question, Guadav, which you asked about 50 minutes ago by now, go watch the Dizzy stream I did a couple of weeks ago, because that's where I go into that question in a lot of detail. But that is a very cool question. It's why I had a mental note of go back to the question about large-scale structure. And I've had that mental note for 45 minutes and I got back to it. Okay, going back to the questions and the comments, what else? We answered spinning black holes. We answered about space-time inside black holes. We had a lot of black hole questions today. That is very cool. I love black hole questions. I warned you all to stay away from quicksand, not to jump into black holes. Okay, we went through black holes and white holes and Hawking evaporation. Did all of these. Let's see, going more questions. We got some CMB discussion when I slipped in the CMB. There was somewhere, I'm pretty sure I've answered all of these by now, somewhere there was a question about baryon acoustic oscillations that I wanted to get back to. Yes. Question asked by John a while ago. With baryon acoustic oscillations in the CMB, what generated the sound waves and at what stage in the early universe were they generated? Love this question. So going back to the CMB, the cosmic microwave background radiation. Now, what we had here was a balance between different things in the early universe. So you have gravity pulling things inwards and you have pressure pushing things outwards. When we're talking about the photons, you have a drag effect between the photons and the baryons. So baryons are just the first atoms, the protons, the electrons that were there at the time when the CMB was formed. So you have this friction where photons are trying to move freely throughout the universe, a kind of photon fluid is trying to move freely, but the photons keep the photons keep I'm going to need a drink before going on there. Let's try that again. The photons are trying to move freely in the universe, but they keep bumping into the baryons, so into the protons and the electrons. And there is this drag effect, the photons trying to go outwards, and the friction between the different things. So here you start getting an interplay where you have gravity and you have pressure. You have gravity, you have pressure. At some point, the universe cools down enough that the photons can break away. The universe cools down enough, protons and electrons clump together. They're now no longer like a gas. They've now actually formed into specific areas. So the photons can break away and start traveling freely. This happens 380,000 years after the end of inflation. So what happens then? Photons break away, they travel freely, and today they give us this map here. We can see the effect of this oscillation of these kind of sound waves. So these oscillations will leave a sound wave in the plasma. And we see this in two places. We see it in the CMB, and we also see it in the average sizes between galaxies. So this battle, gravity, pressure, when it stops, there's going to be this final wave, this final acoustic oscillation that goes outwards. And this leaves an average distance. So it doesn't look like it here, but when we break down the statistical properties, there are regions where there are slightly more red dots and regions where there are slightly fewer red dots. And it's not really about like, oh, this patch is blue or this patch is orange. It's about how far apart the different orange and blue patches are from each other, how correlated they are. So when we break the CMB down into its like main image, what we actually get out of the CMB is what is called the angular power spectrum, which I'm about to show you as soon as I remember which slide it is, this one here. So this is the actual data that we take out of the pretty picture of the cosmic microwave background radiation. Here you can have the angular scale, so what patch of the sky we're talking about, and we have the temperature fluctuation, so how many hot versus cold spots we have on the CMB. The red dots correspond to the data from Planck, the one that I was just showing you. The green line is our best fit to this data. And you can see the green line goes through the data quite nicely. This is lambda CDM, our standard model of cosmology. But this first big peak here, you see there is this big peak, and then the other oscillations, the other bumps. This is what the baryon acoustic oscillations look like inside the cosmic microwave background radiation. So they really are these waves, these big waves, and then the other ones, what happened when we had this interplay of the friction and the gravity pushing and pulling things in different directions. This also shows up on the average size between galaxies, which is what the dark energy spectroscopic instrument is using to calibrate their measurements. Because this is a size that we can calculate theoretically how big this should be. That is a number that you can then pull out in your galaxies, and you can use that to measure distances. So you find this average distance between galaxies, there's a number that appears much more frequently than other numbers, and that is what is known as the sound horizon. So it is the imprint of the baryon acoustic oscillations, and we can then use that to do galaxies. So baryon acoustic oscillations are generated at the time of the CMB, 380,000 years after the end of inflation, and they show up in both the map of the CMB and the map of galaxies, which is very, very, very cool. And I'm giving a 5-minute answer to something that could be a 1-hour stream, because that is a whole very cool topic. Maybe I should do a whole stream about perturbation theory, but broken down, like perturbation theory without any of the equations. That would be a fun challenge. Yeah, I should do that. I'm adding that to my list of streams that will happen at some point. Perturbation theory without the equations, without the math. That will be fun. So basically, why the CMB looks the way it does, why galaxies look the way they do, and how we tie a story from inflation through the CMB and galaxies using quantum effects. Very cool questions, very cool topics. Okay, glancing through the questions again, because I'm still doing my read through from the top. I know there's going to be some at the bottom that I haven't yet seen. Okay, back to where I was. Matteo, I just saw Matteo appear. Hey, Matteo, great to see you here. I didn't realize you'd snuck in like 10 minutes ago. Great to see you, Matteo. We need to catch up. Matteo is a former collaborator of mine. We have 6 papers together. He was on Cup of Cosmology a couple times as well. Great to see you in the comments, Matteo. The point of Hawking evaporation is that you split 2 particles on the horizon. So this is going back to the idea of, can white holes have Hawking evaporation or Hawking absorption? So, comments from Matteo: you split 2 particles at the horizon, you absorb the energetically negatively charged one, and you emit the positively charged one. The concept of charge here is relatively arbitrary, so do not read too much into it. Yeah, positive, negative. Either way, white hole would just absorb and evaporate the particles of opposite charge, so expect some sort of Hawking evaporation to still be there. Yes. Thank you for that, Matteo. I agree that, yes, it would make sense to have some type of opposite process to Hawking evaporation, or even still Hawking evaporation. You're just emitting and absorbing different particles. So yeah, it could be that white holes have also Hawking evaporation in the same way that black holes do. That is very cool. I just see, Gwenda, if you posted your comment again about large-scale structure, thank you for that. I'd already scrolled back up to the top to find it, but thank you for posting it again. I do appreciate that. You're all faster than me because I'm scrolling up to find comments and you're placing them there. Ideally, I need 2 screens open, one with the current comments and one when I can scroll back, and then I would be able to do that and actually jump back. Have I seen that video animation simulating flying through the Dizzy maps? Yes, it is very cool. People have taken this 3D map by Dizzy and got like simulated what it would look like to fly through it, which is really, really cool. And you get to see all of the structure around you. Really, really recommend looking that up and looking at that. It's very cool. Maybe with all these surveys, comment from Paul here, I'm catching up now. Maybe with all these surveys, they can update the Laniakea glass sphere. That would be cool. So you can get spheres with galaxies engraved in it. It's like, you are here, center of the galaxy, or center of this cosmic web thing. It's very cool. I have one. I'm not going to get it now because it's like over there and I'd have to run away. But you can get glass spheres with laser etched cosmic web inside. It is very, very cool. Yeah, whatever. I went back 45 minutes to answer the large scale structure question. It's because it was a very cool question, and I do like to answer all of the questions. If I don't have time, I will answer them next week. But you asked a very cool question, and I had it open in my mind. Go back and answer that question. Okay. There was a good follow-up to the CMB question here. Is the green line the fit of the data or the prediction of the theory? It is the prediction of the theory. So this idea of the green line here, let me just go and find it again. A show on perturbation theory sounds fascinating. Yeah, I'm thinking how I'm going to do that, but I'm adding it to the list of things I want to do. So Paul had a CMB question here. Is the green line the fit to the data or the prediction? The green line is the prediction. This is very, very cool. The green line is not a fit to the data. The green line is the prediction of what our best lambda CDM, what our best model of the universe looks like. And look at how accurately we've gone through this. Look at how accurately we fit the data. So this green line here is not a fit. This green line is a prediction. And this is why the CMB gives us so much information. Like from the CMB, we've pulled out the standard model of cosmology that tells us the numbers that I keep throwing about. You know, these numbers of we have 4.9% normal matter and 26.2% dark matter and 68.9% dark energy. This really comes from this green line that is fitting or that it goes through all of the data points. It is remarkably well described. And this is one of the problems, because we occasionally have some issues in cosmology, like the Hubble tension, where different data sets give different results. But it's quite hard to find a model that goes through the CMB data points as accurately as lambda CDM, our standard model of cosmology, does. So then it's quite hard to try to break our cosmology while still keeping to the CMB. So that is very cool. How accurately we go through those data points. Do I want a football update? Sure. I've not been following literally anything about the Euros, but football update, sure. It would be really cool to discover a hypermassive black hole that started as a supermassive black hole that got so big from consuming its entire host galaxy. Yes, that would be very cool. I feel like at some point, if you have such a hypermassive black hole, yeah, then it becomes an issue, right? Because then you have like a galaxy-sized black hole, and I feel like that would be very big. There's also the thing that gravity, as I've said a few times in this stream already, gravity is weak. Gravity is the weakest force. So in order, even though there is a black hole at the center of our galaxy, we are not falling into that black hole anytime soon, because we are far enough away from it that we don't need to worry about falling into the black hole. And we have a supermassive black hole at the center of our galaxy. So if you want a supermassive black hole to absorb all of its galaxy, we need a lot of time to pass and a really, really, really massive black hole. So yeah, it's something that can happen potentially many years into the future. I think right now it would be, if we discover that, everything we know about galaxy formation and supermassive black holes needs revisiting, because we don't expect to see supermassive black holes that big. But to be fair, we also don't expect supermassive black holes, and yet they are there. So we still need to explain supermassive black holes before we move on to explaining hypermassive black holes. Comment from Matteo about this here. Is a prediction relying on parameters fitted on the data still a prediction, though? Well, it's a prediction in the sense that you start from a model and you vary the 6 parameters in the model until you fit the data. Yes. Was it something that we could have predicted a priori? Not so much in the sense as, it's important to make this distinction. I agree. When we talk about predictions of general relativity, for an example, one prediction was how much Mercury was kind of wobbling as it rotates around the sun. That is a number that you can calculate and then you predict. Now, we didn't predict what numbers we were going to get out of lambda CDM cosmology. There are 6 numbers that we have here. And when we can then you try to figure out which of these numbers best fit the data. Now, Matteo, they are very good points that you're making here, and I know you're here to annoy me. That is always the case, but don't worry, it is a very valid point. So this green line is not so much a prediction that we did a priori with no knowledge. It is what the model gives us when we do incorporate the data. But you could get this model without using the data. So you can generate a billion versions of this green curve, and then you see which one fits the data the best. So I think the difference here is we're not just taking the data points and blindly averaging through them and drawing the best fit line to the data. We are kind of running a billion versions of this green line and then figuring out which one fits the data best. So it's a slightly different process, but I agree that it's not fair to phrase it as a prediction per se, but it is also not just a line that's fitted to these red dots. It is a model that is fitted to these red dots. But yes, that is a slight distinction that is important to make. You got to go. Yeah, we've been on for an hour and 20 minutes. It's very fair that you got to go. This was over time. So on that note, I do believe I've answered everybody's questions here. We've had some really, really cool questions today. So thank you everybody for that. We talked a lot about black holes. And it's nice because last week we talked a lot about gravity, about quantum gravity, about gravitational waves, and I feel like black holes was a very nice follow-up. I also feel like you're all reading the prompts that I put now, which is very cool, because I always have to come up with a new description to the YouTube channel. Short answer for Prath: yes, I will be streaming next week. Back to what I will get to that in a sec. So I always come up with a video description, and I just improvise it every Sunday morning. Like, what do I put here? Let's just put random stuff. And last week, one of the things there was I always put like 2 or 3 prompt questions, just things you can ask me. And last week, the prompts were like, "What are black holes?" No, last week it was, "What are gravitational waves?" And within 10 minutes of the stream starting, somebody asked, "What are gravitational waves?" I was like, haha, you pulled it from the prompt. And today, one of the prompt questions, if you look at the YouTube description, is, "What are black holes?" And we've had a whole stream about black holes. So I feel like you're all kind of reading the description now and actually doing that, which is very cool because then I don't need to go and change the description afterwards. So I'm really glad that we got, yeah, subliminal suggestion. You just see the word black hole and you're like, actually, I'm going to ask that question. I'm going to do an experiment and see if it works next week, because now that I've told you, you know to look out for it. Okay, so we took an hour and 20 minutes today, but there were a lot of really cool questions about black holes. We went on some tangents about baryon acoustic oscillations as well, which was really fun. Some dizzy talk, but it was a lot of black hole questions today, and I really do like black hole questions. They're always fun. So thank you everyone for the questions. This was really, really fun. Cup of Cosmology should be back next Sunday. To my knowledge, there's nothing stopping me from coming back. There is a convention, a sci-fi convention happening in Finland that I'm still debating if I'm going to or not, but I'm probably not going, which means I will be doing the stream on Sunday as usual. So there should be a stream next Sunday, same time as usual. And then in July, there's going to be at least 2 special topics. There's going to be a stream entirely about the paper that I put out very recently. At some point, there will also be a stream about ups and downs of academia, the good, the bad, the stuff you don't know, the stuff you don't want to know, and the good stuff as well. And then at some point over the next few months, I'm going to do an introduction to perturbation theory without doing any equations. I have no idea how I'm going to do that, but that is going to happen now. I have to make that happen. That is going to be a fun one to do. So there are more streams coming up. I currently do not have any planned breaks in the streams in July, but of course I'll let you know if I do have to cancel any of them for whatever reason. But we should be back online, or I should be back online next Sunday. So that is 8 p.m. if you're in Finland, 7 p.m. if you're in the rest of Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is going to be in your own time zone. There's also some fun stuff happening on Cup of Cosmology webpage. There have been a few minor updates. Feel free to go and check it out as always. So yeah, thank you everyone. This has been super, super fun. It's been really nice to have all of your questions and all of your comments. And so much interaction, so many cool questions. I love that you're all here. Like the video if you haven't done so, leave a comment, subscribe, all of the usual YouTube stuff. You know how YouTube works. It really does help when you do that. So Cup of Cosmology should be back again next week, same time as today. I hope to see you all then. And I hope in the meantime, you'll stay safe and take care of each other.